Okay, so the next homework is a little bit long. It's one of these graphing problems where we have to do some algebra. We want to understand a certain kind of function, and you have to understand a lot of things to get a really good graph. So I made this one worth 100 points because we have a lot of different parts that work together, but shouldn't be too bad. It just takes a while, and you just have to do it. So I'm going to break this into a few different pieces. We want to understand a couple of different aspects of a problem. Well, first of all, let's say what is a rational function, and then this video we'll talk about domain, which those are the valid inputs, and then at the invalid inputs, we're going to have either holes or vertical asymptotes, and we'll say when do you get which and what do you do about it, and that'll be this video. And then the other topics, it's like horizontal and oblique asymptotes, that's like in behavior, and then both of those are going to be relevant when we start wanting to graph these things. And yeah, that's kind of all that we're going for here. So what is a rational function? A rational function is just a fancy name that we gave to things like this. So it's a rational function f is a function which has the particular form p of x divided by q of x for or sorry, not, I'm going to say q. Well, if the denominator is the zero polynomial, then the domain is the empty set, because that'd be really bad. If the denominator were zero all the time, then that's just an undefined, that's just a function with no domain. There are no valid inputs, and so that function wouldn't be able to do anything. But if q is not the zero polynomial, well, just for one example, this is kind of a simpler example. This is just, I just want to show you that this, just plain old polynomials are examples of rational functions. Those are the ones that we already studied, and polynomials are already pretty sophisticated, and we have to do a lot of work to factor and find the zeros and all that. Some polynomials are more complicated than others, and yeah, you might need computer software to approximate where are the zeros of a polynomial. So so for rational functions, it's more general. So sure, we could just divide by a constant, and then the end result is a polynomial, as long as that we're dividing by something that's not the zero function. But there are other things too. So example, this is also totally fine. The numerator could be a constant, like 1 or 2 or -7. So this thing, f of x equals, if it takes the form p of x divided by q of x, then sure, there's this function 1 over x. Among all the rational functions that are actually kind of, not just old news, but actually there's something going on here. Well, the simplest thing you could do to make it more complicated is you could have something like 1 over x. And now we're in business, and that's one you've probably seen before. But we're gonna, pretty soon deal with all sorts of animals. So, more typical book problems would be like f of x equals 3x plus 7 over x squared minus 4x plus 4. I don't know, just whatever. So we want to understand domain. What happens when we're not in the domain? What happens nearby? I claim that for a rational function, it's going to be one of these two things. That's what this video is going to be about mostly. And we'll just say a little bit about that, but as sort of a point of hopefully you've investigated the function 1 over x at some point, because it's really going to give you a very good intuition about understanding vertical asymptotes and holes in general. So that'll be pretty important. So let's sort of go to the other side. So all right. So what do I want to say here? Yeah, so let's just look at 1 over x as sort of an example. Let's just review that real quick. And then that'll kind of motivate some of our definitions. So if you understand this one, you're kind of halfway to understanding the general case. It's just you have to understand what's doing what and why is that happening. So okay, so a lot happens near x equal to 0. So maybe I'll just only go out to x equals 2 or something like that. X can go all the way out to plus or minus 2. But some really interesting things happen for even, I want to make this scale a little bit. Sometimes I take a step back to see what I'm doing so it's really evenly spaced. So let me try to be a little bit more careful with that. Okay, so try to keep this line mostly straight, and that's 1, and then that's 1, roughly 2. So that would be 1/2, and then I'm only going to go up this far, but you could make an even bigger graph. Let's see, 4 is down, minus 4 is down here. And if you're not convinced by what you see here, you can always plug in even more x values. The ones that are really close to 0 are actually pretty interesting, but let's just plug in some x's and y's. So x, well, 1 divided by 0 is undefined. That's a good place to start. So these are not quite these are a little bit out of order, but as long as I carefully read the x value and then put it with the proper y value, it's still a table of values. It's just not in any particular order here. It's okay, so the point is I've got 1, 1. I've got when x is 1/2, y is all the way up here at 2. When x is 1/4, y is all the way up here at 4. If I did 1/10, I'd be up here at 10. And if you plug in enough values, you'll see that it basically, you can keep going to the left, but you can never quite get to the y-axis. It just keeps going steeper and steeper, and maybe I could actually plug in x equals 2 and I get a y equals positive 1/2. That's so for x very large, interesting things happen, and then for x very close to 0, other very interesting things kind of happen. So x is negative 1/2, then y is negative 2. X is negative 1/4, y is negative 4. So very famous, but it's also very instructive. It kind of sets the stage or sets the tone for what kind of happens in general. So so what happens so here's kind of the relevant facts about this that kind of generalize to other cases. And the more you think about this, this is the kind of thinking that you do a lot of in calculus, but you can start thinking about it now. Calculus is just kind of, a lot of calculus is about asking what happens when x is very close to the endpoint of the domain. So we've got x equals 0. And we've got f of x is actually, we're getting all these negative numbers to the left of x equals 0. This bad point is not in the domain. And we're getting positive numbers. So basically what we have is we have 1 divided by it looks like this. You have 1 divided by a positive or negative small number, you end up with a positive or negative big number. So kind of the summary here is so sorry, I meant to move here, but it's hard for me to write without blocking it. Okay, so here c is equal to 0. That's the x value that's not in the domain. So you have this point that's in the domain, and if you also have that, what happens, the numerator is either a constant or the numerator approaches some number. So so basically here we have 1 divided by 0, quote unquote, is what's happening here. The numerator is when you plug in 0, the numerator wants to be 1, but the denominator wants to be 0. Well, that's the classic thing that looks like, that behaves just like 1 over x. If you divide like just one particular positive or one particular non-zero number by a number that's very close to 0, you get big stuff, and that just kind of is what happens generally. It behaves a lot like this. So it's 2 divided by 1/1000th is going to be 2000, big numbers. So that's so we can kind of have a table of these things. And maybe I'll write down a summary later. So what I want to do is I want to compare that to this other thing. So you can pause it, but I'm going to use almost the same graph for almost the same function. I'll explain this in a minute, but let's make the function x plus 4 divided by x squared plus 4x. And let's see what changes here. Well, I had to factor an x out of the denominator. The numerator has an x plus 4, but the denominator also has an x plus 4. Oops, sorry, x is not allowed to be okay, so this is almost the same function, but something really, really weird happens. I claim that this is what happens, but let's slow it down and let's talk about it. All right, so new function. But it's almost exactly the same function, but what's the difference here? Well, okay, we have the function x plus 4 divided by x squared plus 4x. Okay, so an x factors out in the denominator, and for so or you can even write it that way if you prefer. So there's this stuff cancels, but you still have, anytime you cancel factors with division, you still have a 1 left over. So it looks like 1 over x, but anytime that x is not equal to 4, that cancels. But anytime x is equal to -4, this is actually 0 divided by 0. So why? Because the original function, the way we actually defined it, says that the function itself is totally undefined, just at that one x value. Everywhere else, it's totally, well, -4, it's undefined, and then you're dividing by 0 again at x equals 0. Well, okay, so everywhere except for x equals -4, get this. So that's what we get here. Okay, so this says that if you're dividing by 0 at x equals c, but then the numerator has, but if you can cancel it with an identical factor from the numerator, and then what's left over is no longer dividing by 0, then it's behaving just like this function here. It's just there's a hole in the domain. The original function is 0 over 0, but then times some other stuff, and that other stuff says what the overall shape is. Usually this cancels. Just at that one specific bad point, you get a hole. So it's a little weird, but what happens is, well, what you try to plug in -4.1, then everything's fine. You'll get you'll get a number like, you'll get 1 over negative 4.1. You'll get something here. But if you try to plug in exactly negative 4, it's 0 divided by 0, and there's just, you can't do anything at all. So that's it. So so if you're so if you have, like 1 over x, and you approach x equals 0, the numerator approaches 1, the denominator approaches 0, that's a vertical asymptote. If you have 0 over 0, because it looks like x equals negative 4, then you keep factoring the numerator and the denominator, and then you get so if you factor a bunch of stuff out, and then it looks like a constant. So in this case, you factor out a bunch of stuff, and then it looks like here c is equal to negative 4. You factor out a bunch of stuff, and now it looks like you plug in negative 4, it looks like negative 1/4. And that looks like a hole. So let's just do some more examples. I think with repetition, it gets sometimes seeing the general case, the easiest way to do that is just to do a lot of specific ones. So yeah, so let's see here. Okay, yeah. All right. Okay. Okay, so find the domain. I think we've already done problems exactly like this, but that was a while ago, and it's relevant again now. We'll do it again. And what do we do with those? Well, Okay, so I'll give you maybe a couple other ways of thinking about this. At any rate, there's our 5x, there's our 6, there's our x squared, so that looks good. So the whole caution with finding the domain of a function is that you can factor, but you don't want to cancel anything right away, because the original expression, you have to check whether it's you can't cancel these two things until you know that you're in the domain in the first place. So what I'm saying is if x is -3, the entire expression is 0 divided by 0. If x is not -3, then those two things can cancel, and then you're okay. But always kind of look at the original. Before you cancel anything, always look at the original before you start jumping to conclusions. So for the domain, what happens, we have all of this here. X does not equal -3, and x does not equal to -2, and usually we'll want this as well, the number line says that this number is is the farthest to the left. Now it should look like this. So here are our two problem points. Each of these, because it's a rational function, the finite numbers in the middle where you're not in the domain, they could be one or both of them, could be a whole one or both of them, could be a vertical asymptote. So sometimes like if I call the domain D, so if x is in the domain capital D, then the function looks like this. So the only problem is x is not allowed to be -3. And yeah, sure, x is not allowed to be -2 either. But what's remarkable here is that this simplified expression looks okay when x is -3. So it's those 2 points. So you simplify the function. You keep in mind that once your domain restriction, once you have your domain, it has to exclude those numbers. Then, if the simplified function where you cancel the stuff, at some points you get a vertical asymptote because the denominator has more zeros than the numerator left over, and then Okay, so either the 0 in the denominator, either that cancels with something in the numerator, and that just means that that 0 in the denominator is, well, it's just something that factors and cancels most of the time, but technically it's 0 divided by 0, which is undefined, which leaves you with a whole. So that's not as big of a deal, but it's technically a problem, and the graph itself is going to have a hole at x equals -3. But this extreme case where there's just kind of the whole thing just blows up and there's nothing you can do about it is when it really behaves. This x plus 2 in the denominator, there's nothing you can do about it. It doesn't cancel with anything. It's just there forever. It behaves just like 1 over x at 0. But here it's at x equals -2. And so for the vertical asymptotes, that's the places where the denominator is 0, but the numerator does not approach 0. Or if it did, we already canceled everything. Okay, so it's I want to save the top half for later, but so I want to simplify this and illustrate the picture a little bit. So here, something that could happen is maybe both the numerator and the denominator are 0 when x is equal to 0, but there's an extra copy in the denominator. So that still behaves like 1 over x. There's an extra x minus c, like, these could have been x plus 2 times x plus 2, but if it's just x, then there's an extra x. So there are two factors that make the denominator 0, and that's x and then another x factor. The opposite is how does this one behave? So let's examine what if the numerator had more x's. X squared divided by x equals x times x divided by x times 1. Technically, if x is 0, this expression is undefined. It's 0 divided by 0, which is no good. Well, try to plug 3 into this. You get 9 over 3, which is 3, which is just the thing that you started with. You just get x, but x is not allowed to be 0. So this one looks like the 1 over x function because there was an extra, just the denominator wins. There's an extra x minus c in the denominator, so it's a vertical asymptote. And that's the general behavior. So take a note of the domain of the original function. Then you simplify the function. That new expression That new function, as long as you take a note of the new domain, that function is equivalent to the original expression. And any domain restriction that was tacked on, well, we canceled out all the zeros in the denominator successfully. We found that we had extra factors in the numerator to cancel those out, and that was really good. But for all time, we're left with this domain restriction. The original function was not defined when x is equal to 0. So technically, if we want to understand the original function, we have to put a hole there. It's just, you put 0 divided by 0. That's no good. So both of these are 0 divided by 0 when x is equal to 0. But what happens when x is close to 0? This one looks like 1 divided by x. This one just looks like x. In another example, h of x is equal to x divided by x, which equals the function which is 1 when x is not equal to 0. Similar behavior here as well. So that's a function that's just x is not allowed to be 0, but y is always 1. So you get a hole when all the x minus c's cancel. But if the denominator has an extra factor of x minus c that doesn't cancel, and then the leftover numerator is some non-zero value when you plug in the x's, that's a vertical asymptote. But if all of the x minus c's in the denominator cancel with x minus c's in the numerator, and then the resulting function is something that's not divided by 0, then that's a thing that you can evaluate it, but you have to put an open circle representing the fact that the original function is 0 over 0. It's just you canceled all of the factors that led to that. So that's roughly the idea. So that's kind of long enough, so let's call it.